Hello students, welcome to EPG Patashala. I am Dr. Gayatri, Assistant Professor in Center of Advanced Study in Crystallography and Biophysics, University of Madras. The module we are going to see now is on small angle X-ray scattering from the paper Biocrystallography. The objectives of this module are: we will first have an introduction about what is small angle X-ray scattering, what is the significance of small angle X-ray scattering, what are the general protocols one has to follow while doing data collection and processing, and also what are the key features in the patterns obtained from small angle X-ray scattering, and what are the applications and the present scenario of small angle X-ray scattering. We will cover all these objectives one by one. Small angle X-ray scattering is a non-destructive method for investigating the nanostructures ranging from 1 nanometer to 200 nanometer in size. Small angle X-ray scattering can give the information on wide aspects like the aggregation, the molecular mass, particle size distribution, the radius of gyration, folding and unfolding of the macromolecules, that is a conformational state, and also about the oligomeric states. It also gives details about the stability of the molecule, the extended conformations, the flexibility of the domains, and also it is used to characterize the structure of polydispersed systems. It also helps to find out the low resolution three-dimensional shape reconstruction. Let's have a look on the brief history of the development of small angle X-ray scattering. It was first built by Professor Otto Kratky in collaboration with Anton Paar in the year 1957. Then he developed a compact camera in the year 1981. In 2003, they introduced SAXS that features X-ray beam monochromatization. In 2012, several new features have been included in the SAXS and they named it as SAXS space. In the year 1938, Guinier postulated X-ray small angle scattering of an isolated particle as particulate scattering. Small angle X-ray scattering studies are used to distinguish three important cases. One, the monodispersed systems, that is the identical particles, polydispersed system, which have same chemical composition but different in size and shape, and also to study the mixture of compounds which are different in chemical composition, size, and also in the shape. Scattering in general gives an inverse relationship between the particle size and the scattering angle. The results obtained from the SAXS are representative of the entire sample. It ideally complements the methods that only provide the local information. Small angle X-ray scattering also stands out for enabling the studies on biological samples in their native state. One of the major applications of small angle X-ray scattering is SAXS. We will see in detail about the SAXS as we move further. Another important discipline or application of small angle X-ray scattering is grazing incident small angle X-ray scattering, and this method is used for investigating thin film samples and also nanostructured surfaces. Electrons resonate with the frequency of X-rays passing through the objects, and they emit coherent secondary waves which interfere with each other. The spherical particle and the wave scattered from two identical points as shown in this figure, they diffract at an angle of 2 theta with a path difference of lambda. If the scattering from all points are considered in a 3-dimension, then the superposition of the waves with all possible phases will essentially lead to low scattering in the direction of 2 theta because of the destructive interference. If we consider the smaller scattering angles, then the phase difference becomes smaller and the waves will begin to reinforce one another. So the maximum scattering will eventually be observed in the direction of zero scattering angle where all the waves are exactly in phase. If the path difference lambda will occur at smaller scattering angle, that will result in a narrower scattering curve, the curve 2. For particles that are huge when compared to the wavelength, X-ray small angle scattering occurs. In the case of for anisotropic particles, one has to calculate the scattering for every orientation and average the results. One of the different techniques for calculating the scattering curve involves the distance distribution function of electrons. During data collection and processing, one has to keep in mind the certain points. X-rays are sent onto a sample and are scattered by its particles and also by its domains, thereby producing a scattering pattern which is characteristic of the sample's structure. The scattered X-rays can be resolved at different angles. When X-rays fall on molecules in solution, the spherically averaged intensities are recorded, which is an isotropic pattern. The radial integration of the pattern will result in one-dimensional small angle X-ray scattering profile. Analysis of this profile will provide information about the size of the molecule and the shape of the molecule in solution state. In the case of anisotropic particles, the scattering for every orientation must be calculated and the average of results must be taken. To calculate the scattering curves, one has to calculate the distance distribution function of electron, which is generally obtained from the geometrical considerations. In SAXS, one resolves the small angles to measure the molecular structure that sizes up to 200 nanometers. Smaller structures such as the crystal lattices on the atomic level can also be analyzed by resolving the scattered image. X-rays at wider angles, that is approximately the 2 theta is greater than 10 degrees, wide angle X-ray scattering is used. Moving on to selection of the beam shape, the X-rays have to be collimated first, either into a line collimation or a point collimation. Both have their own advantages. Line collimation is ideally suited for measuring non-oriented isotropic systems, especially weakly scattering samples such as the diluted dispersions and emulsions. Point collimation is a very good choice for analyzing oriented samples, solids with inhomogeneous structures, as well as nanostructures surfaces by GI SAXS. One need both collimation modes in order to optimally cover the entire range of potential small angle scattering applications. Use of synchrotron radiation has wide application in SAXS experiments. High intensity X-rays that are available at synchrotron radiation provides two major benefits when compared to the lab-based instruments. The greater X-ray intensity allows the measurements to be performed at a greater separation between the sample and the detector, which allows the access to much wide range of length scales. The high intensities of X-rays at the synchrotron radiation means that the measurements can be made much faster, allowing the structural investigation of non-crystalline materials to study under in situ conditions. For example, the fluid flow at high pressures, and also one can do the experiments by varying the temperatures. Small angle X-ray scattering using synchrotron radiation will provide reliable access to millisecond or even shorter time scales that are essential for understanding the kinetic processes such as ordering and alignment in liquid crystalline materials, and also to study the structural changes happening in the system. In the case of dilute and monodispersed protein solutions, the scattering profile that's generally given by a symbol I of Q is related to the probable distribution of interatomic distances within the scattering particle by using its Fourier transformation. In other words, the net intensity is proportional to the scattering from a single particle that is averaged over all its orientations. The distribution of distances within the particle averaged over all orientations is a one-dimensional function. The curve I can be obtained from the distribution by using a Fourier inversion as shown from this equation. For rod-like particles, multiplication of the scattering curve by 2 theta results in the cross-section factor, which is helpful in calculating the radius of gyration. It is a curve depending on the shape, size and electron density distribution within the cross-section. In a case of plate-like particles, multiplication by the square of 2 theta will give the thickness factor that depends upon the particle thickness and electron density distribution perpendicular to the particular plane. Scattering curve in general is represented by I of q. It comes from the subtraction of the buffer density from the sample density. I of q is a function of the momentum transfer. In general small angle X-ray scattering experiments, the intensity is expressed as a function of the scattering vector that results from the photon of wavelength lambda scattering off the sample at an angle 2 theta. For a macromolecular studies in solution, the intensity distribution of the macromolecule must be obtained by subtracting the buffer or the solution profile from the total profile. Let's say some of the terms which are being used or one should know while using small angle X-ray scattering. Distance distribution function. One can obtain the distance distribution function from the I of q by using an inverse Fourier transformation where one involves an integral of I of q from 0 to infinity. But the scattering data can only be measured by a finite small q range, and hence this transformation can be done analytically and one has to use an indirect transformation method. Distance distribution function is also referred as pair distance distribution function. In short, it is called as PDDF, which is the weighted atom pair distance histogram. This profile will determine the forward scattering intensity, the radius of gyration, and also the Dmax. In order to evaluate the sample monodispersity, I0 is very important. In Guinier plots, we will see what is a Guinier plot later. In Guinier plot, the deviations from linearity are observed due to fourth interparticle interference and protein aggregation effect. The dilute monodisperse protein systems obey the relationship K is equal to I0 divided by Mr times C. Mr is a relative molecular mass of the scattering protein. C is the concentration of the protein in terms of mg per ml. K is a constant. The important feature of small angle scattering method is that it allows the determination of mass per unit length for rod-like particles and mass per unit area for plate-like particles. Various conformations of dimer formations can also be extracted from PDDF profiles. This graph shows the different form two dimers. Molecules can form a dimers in a different way. This can be extracted from the profile pattern. Let's have a look on the outline of SAXS data analysis. The experimental intensity is usually fitted in order to determine the density, the size, the shape, and also to study the internal structure of the scatterer, as well as the interaction between the scatterers. Small angle X-ray scattering intensity depends on the structure factor, form factor, and also on the electron density of the scatterer. Form factor gives the size distribution and shape of the particle. Structure factor is greatly influenced by particle-particle interaction, that is the interaction between the scatterers, the clustering and assembly of the particles. Another term is atomic form factor, which is given by symbol P of Q. It represents the particle shape or the interference pattern and is directly related to the size of the particle. It also provides the information about the shape of the particle. It's a function of amplitude and the particle volume. For sphere, the equation is very straightforward, but for cylinders it becomes more and more complex. The equation for sphere is shown here. The theoretical intensity of a particle is the function of the form factor, electron contrast, and particle volume. The total intensity profile is the sum of each particle intensity for monodispersed particles and the weighted normalized summation for polydispersed particles. Structure factor. Structure factor will provide information about the interaction between the particles which can be obtained from the scattered intensity. Let's move on to some of the key features of small angle X-ray scattering pattern. From the scattering curve, it is possible to obtain several parameters. The oscillations in the pattern is a very good indicator of monodisperse size, and the correlation peak is an indicator of particle interactions. The small angle X-ray scattering profile has three important regions, or one can say three distinct regions from which information may be extracted. The first one is a Guinier region, second is a Fourier region, and third Porod region, which is clearly shown in this graph. Where the Guinier region will reveal the size, Fourier will reveal the shape, and the surface information can be obtained from the Porod region. Let's see each and every one in detail. In the case of Guinier region, the experimental radius of gyration may be approximated by fitting a line to the neutral log of the intensity as a function of square of the scattering vector. The fractal behavior can be extracted based on the indicators. Generally, there are three indicators which are shown here: for smooth surface, for rough surface, and for clustered particulate structures. Q-PA -4 is used for smooth surface, Q-PA -3 for surface fractal, that is the rough surface, and Q-PA -2 for mass fractal, that is either dendritic or clustered particulate structures. Shows the different plots and the different shape of the curves, like the oscillations in the pattern or the correlation peaks in the pattern will give each and every information. The oscillation, as we saw, it indicates the monodispersed size of the particles. Correlation peak is an indicator of particle-particle interactions, and the fractal behavior can be obtained for different surfaces. Q-PA -4 for smooth surface, Q-PA -3 for rough surface, and Q-PA -2 for clustered particulate structures. From the Guinier region, the radiation of gyration can also be obtained. Radius of gyration is the root mean square of the distances of all electrons from their center of gravity. Also, radius of gyration is the average of square center of mass distance in the molecule weighted by the scattering length density. It is also the measure of overall size of the macromolecule. The radius of gyration will be greatly affected by the aggregation of the particles. It is also affected by the polydispersity and improper subtraction of the background or the buffer density. Moving on to the Fourier region, the pair distribution function may be determined by an indirect Fourier transformation. It is also the measure of overall size of the molecule. The radius of gyration will be greatly affected by the aggregation of particles. It is also affected by the polydispersity and improper subtraction of the background or the buffer density. It is an intuitive measure for the spatial extension of the particle and is proportional to square root of the slope of the tangent in the Guinier plot between the limits when 2 theta tends to 0. Moving on to the Fourier region, the pair distribution function may be determined by an indirect Fourier transformation. The Fourier region provides information regarding the shape of the particle. In this region, the pair distribution function may be determined by an indirect Fourier transformation like we saw earlier. This is the equation for the Fourier region, which is used for finding out the shape. This equation gives the distribution of electrons averaged over a particular radius. The curves are used to determine the general particle shape, provided all the particles in the sample are of similar shape. It's a very important criteria. Then the third region is a Porod region, which gives information about the surface and also the surface to volume ratio. It also gives information about the specific surface estimation for compact particles. The Porod invariant, which is given by the symbol Q, is shown in this equation, and surface to volume ratios are also given here. The log of the form factor is proportional to Q-PA -4 for the particles with uniform density. In a case of a Porod plot, that is a plot of Q-PA 4 I of Q versus Q, provides information about the Porod volume, the molecular weight for compact particles at high Q values where the asymptotic behavior dominates. Kratky plot is another important feature when working with small angle X-ray scattering. It helps you find out whether the molecule is folded, unfolded, or partially folded, especially when we are working with proteins. It is a graph of q square into I of q versus q, which is termed as a Kratky plot. As I said, it is a useful tool, especially for protein analysis and also to determine whether the disordered states are present in the sample or whether the protein is unfolded or it is folded. It is actually a good indicator of protein folding and unfolding states to distinguish between the protein folding and unfolding state. Globular proteins follow the Porod's law and they are generally bell-shaped. The graph of Kratky plot is shown here for the reference. Reconstruction of three-dimensional shape from the one-dimensional small angle X-ray scattering data is an important feature and very crucial task. Three-dimensional shape reconstruction from the one-dimensional data is characterized as ill-defined problem which could be solved only by regularizing the fitted models. Based on how the model fits the shape of the molecule, whether pear shape or they are rod shaped or dumbbell shaped, one can distinguish based on how the data is getting well fitted or well reconstructed. Small angle X-ray scattering pattern arises from the shape and also from the interaction of the scattering objects. Most small angle X-ray scattering analysis simply give the pore or particle size and the shape information. It is also possible to generate a representative morphology that has the same scattering properties as that of the sample. We just have a look on what are the wide range of sample holders that are available. These are the holders which are available in Anton Paar. Mu cell, it is used for lowest sample volumes, and flow cell for automated sampling. In the case of viscous and powder samples, paste cell is used. Roto cell is for averaging microcrystalline domains and tube cell is for disposable fluid pathways. Auto samplers for liquids and solids are also available. For high throughput screening of up to 192 liquid samples, ASX auto samplers can be used. For multi-purpose studies, Vario stage can be used. Let's have a look on the applications of small angle X-ray scattering. It is used to study wide properties of materials and also to study the structures of biological and non-biological molecules either in native form or in a complex form. One of the main applications of small angle X-ray scattering is SAXS, which is used to study the biological samples. It gives information on the size and shape of the macromolecules in a solution state. It also gives details about the radius of gyration, molecular weight of protein and also protein complexes. It also gives information on the conformational changes that happens in a protein upon ligand binding or during protein-protein interactions. One can also study the conformational changes in the protein upon changing the temperature and pH. SAXS is also used to screen the buffer conditions and to monitor the folding and unfolding process that happens. SAXS is extremely sensitive to study the overall shape of the macromolecules. SAXS is extremely useful to study the flexible proteins as they are very challenging to crystallize. SAXS studies are used to distinguish three important cases like we saw earlier in the lecture, to study the monodisperse systems and to study the polydisperse systems and also to study the mixture of molecules. It may also be applied to multiphase systems as well as porous materials. Kinetic study and time-resolved SAXS are of great usefulness for the study of conformational changes. Small angle X-ray scattering is very useful and it provides information on fast timescales and it also gives information on steady-state structure and also on the kinetics. There are several applications, as we saw, there are several applications for the SAXS. One of the major application is BioSAXS. It tells about the shape and size of the protein in solution state. It is used to calculate the three-dimensional envelopes. It is also used to study the protein folding and unfolding states. The another major application of small angle X-ray scattering is GI-SAXS, which is used to study the structure of nano-structured thin films and also to study the surface roughness. The mechanical testing can also be done in order to study the structural changes of polymer foils and fibers induced by the tensile stress. And one can also do the temperature dependent structural studies, where one can vary the temperature from -50 and even to about +50 degrees Celsius, depending upon the experiment requirement. In addition to these applications, small angle X-ray scattering have also wide applications in colloidal dispersions, nanocrystals, in paints, inks, and also in sunscreens. They are, repeat, they also have applications as surfactants, as emulsions, and also to study the biological materials, to study the nanocomposites. Polymers and fibers can also be well characterized by using small angle X-ray scattering experiments. Moving on to the liquid crystals, they have wide applications in liquid crystal displays and also in drug delivery systems. GI SAXS is used to study the thin layered films, that is, they have a lot of applications in nanostructured surfaces and also to study the nanoparticle superlattices. The mechanical testing can also be done in order to study the structural changes of polymer foils and fibers induced by the tensile stress. And one can also do the temperature dependent structural studies, where one can vary the temperature from -50 and even to about +50 degrees Celsius, depending upon the experiment requirement. In addition to these applications, small angle X-ray scattering have also wide applications in colloidal dispersions, nanocrystals, in paints, inks, and also in sunscreens. They also have applications as surfactants, as emulsions, and also to study the biological materials, to study the nanocomposites. Polymers and fibers can also be well characterized by using small angle X-ray scattering experiments. Moving on to the liquid crystals, they have wide applications in liquid crystal displays and also in drug delivery systems. GI SAXS is used to study the thin layered films, that is, they have a lot of applications in nanostructured surfaces and also to study the nanoparticle superlattices. One of the present scenarios in small angle X-ray scattering is by coupling the small angle X-ray scattering and molecular dynamic simulations. It is called as MD-SAXS. It has tremendous potential and it is very useful in structural analysis and also to study the complex formation in macromolecules. Small angle X-ray scattering technique details the folding patterns of these complexes or the structures, while molecular dynamic simulations will model the movement between the states. By combining these two, that is the molecular dynamics and small angle X-ray scattering, may hold the key for furthering the study of nanoparticles and also helps to overcome the informational losses in SAXS experimentation due to spherical averaging and determining the theoretical profile, while retaining the inherent experimental flexibility of structures and also the states. Further, advances in small angle X-ray scattering such as time resolved kinetic studies and the potential for super resolution will only further enhance the capabilities of molecular dynamics coupled with small angle X-ray scattering. So students, Let's summarize what we have learnt in this module on small angle X-ray scattering. We saw small angle X-ray scattering as wide range of applications on the study of materials and their structures. Three-dimensional structures can be obtained from a low resolution 1 or 2-dimensional profiles from the SAXS experiments. For higher resolution profiles, SAXS is coupled with molecular dynamic simulation, which has tremendous scope in the study of biological and also in non-biological materials. Thank you for watching.